All right. Before we get started, just a reminder: project presentations start on March 16th, Tuesday, March 16th, which is now just over 2 weeks away. So again, make sure that that doesn't sneak up on you. I have the schedule posted. And remember, you can, there's that folder on Schoology that has all the information I've given you up to this point. But again, those project presentations start on Tuesday. By the end of class today, I'll show you how you design your test, and you have an opportunity to test questions. I'm having those. I think we should, if you want to have test questions done, do it by Friday. So that's what we got homework-wise. Where I want to start is I want to start with a couple warm-up questions based upon what we did last time. The last time we did the stair lab, right? And I want to ask you a few questions about this. So, while climbing the stairs, did you do more work if you were going fast or slow? Did you output more power if you were going fast or slow? So tell your partner what you think in both of those cases. Did you do more work if you were going fast or slow climbing the stairs? Did you do more power if you're fast or slow going up the stairs? So tell your partner what you think about that. And if your partner's not here, just talk to somebody in there. Thomas, what do you think? Did you do more work if you were going fast or slow? Say what? Slow, you did more work doing slow. Why? You're taking your time, set up, so more work to go slow. Gabe, do you agree you did more work if you're going slow? 1A. No? What do you think? More work if you're going fast? If we got more work if you're going slow, more work if you're going fast, what do you think, Greg? It was the same amount of work. Why was it the same amount of work? Yeah, going the same distance, you were lifting the same force, right? If you look back at if you look back at the these data tables, right? Remember, the work was the same. You were going high, going up the high steps or the low steps. The work was the same all 3 times. The work, it doesn't matter. The only thing that matters for work are force and distance. Speed does not matter, right? So you did the same work in either case. Rowan, did you do more power if you wrote that? Yes, that makes sense, because remember we said power is the rate you do work. So you're doing the same work each time, but if you do it faster, that's more power. And again, what are the units of power? I'm sorry, what did you say? I couldn't say. Somebody had a bad weekend. All right, so you have a little more power if you go fast and slow. Okay, now let's say that instead you're going at a constant speed. Do you do more work if you go halfway or all the way? Do you do more power if you're going halfway or all the way? Again, assuming that you're going the same speed. Tell your partner what you think about 2A and B. What do you think? All right. Kylie, more work if you go halfway or the full way. Why? You're right. What's different about going the full way? You go further, right? More distance, right? So more work if you go farther because there's more distance. Grant, Trey, what do you think? Okay. more power if you go halfway up the floor. Why? Okay, so you're saying that you're working for more time. Okay, fair enough. Well, the more time meant more power. Do you agree, Camille, that you do more power if you go higher? Yeah, you all agree. Well, you go higher, right? So it is more time, but it's also more what? More distance. So you're going to do more. If you go higher, you're going to do more work, but you're also going to do more time. It's going to be the same power, right? Remember, power is the rate. Power is the rate that you do work. If you're climbing the same speed, you're doing the same amount of power. Right? So power has nothing to do with how much work you do. Power is just the rate at which you do that. Okay. So with that in mind, I'd like to talk about the notes from last time and then expand on those a little bit. So pull these out if you have them. Here we go. All right, so remember we just kind of started last class by summarizing, or ended last class by summarizing what we talked about. We talked about how work is force times distance. There are two categories: work against a force, work to change speed. Measure work in joules, right? We talked about power as the rate that work gets done. Work divided by time measured in watts. And then we talked about a new definition, right? The definition of energy, which is the ability to do work. And we said that there are two ways that you can have energy. You can have energy of motion, which we call kinetic energy, or we can have energy that's stored. And we talked about three ways to store energy: gravitationally, chemically, and elastically, right? So I think I showed you last time about if you stretch a rubber band, why are you storing? How is that an example of storing energy? Because it's tension, and if I let it go, right, it has the potential to move, right? So it can cause something to move later on, right? So that's kind of the example. Then I talked about gravitational potential energy. If you lift something, right, and then you let it go, when you lift it, you're storing energy that's going to be used when eventually you let it go. I want to give you one more equation that we're going to use, and then we're going to try some practice with this. So that we've now defined work, power, and energy, but we got to connect them together, right? And what we're going to say is we're going to talk about something that's called the work energy theorem. And the work energy theorem says that whenever you do work, you change the energy. And the way I say this mathematically is work equals delta E. That's the equation. What does delta mean again? Change in, right? So what happens is whenever you do work, you're going to cause the energy to change. So we now have 5 equations, right? We've got the work equation, we've got the power equation, we've got kinetic energy, we've got potential energy, and now we have this work energy theorem equation. What I want to do next is I want to spend some time trying to apply these different situations. So I'm going to start by handing this out. When you get this, I want you to see if you can try number 1. when you get this, go ahead and try question number 1. All right. Sam, can I ask you how you did part A?
I just did 1.3 times 2.5 time and 9.8.
Yeah, good. So the mass, right? We know the mass is 1.3. G, remember, G is always 9.8. And the height of this thing is 2.5. Do you have an answer for that, Sam?
31.85.
And I don't think I said this already, but energy is also measured in joules. So capital J. All right. So that's how to find the potential energy of the apple. Now we're gonna have to think back a little bit to figure out work, right? We kind of did this sort of calculation last time. So work we know, right, is force times distance. But what's my force? It's what? Not distance side mass. Yeah, right. We gotta say, so when you're lifting something, right, what would be the work required to lift it to that height in the air, right? If you're lifting something, you're doing work against a force. Against which force? The force of gravity. So we got to start by finding the force of gravity, which is the mass times 9.8. I don't know, what is that? 12.74. So now that's my force, and this is Newton's, right? So that's my force. And now I have a distance of 2.5. And magically, I think what you get out of that is that. Coincidence? I think not. Why not? Why does it make sense that those two answers are the same? Go ahead. Right, so where did the energy come from, at least if we think about lifting it, right? The energy came from work, right? What did we just say? We said work is changing energy, right? So if you take something, like imagine an apple sitting on the ground. If you take the apple and you lift it up somewhere, you're doing work on it. But when you do work, what are you doing? You're changing the energy, right? If you're changing the energy, any joule of work you do has to turn into some sort of energy. So in this case, your answer makes sense because work equals delta E. The work you do on the apple has to be converted to energy. All right. When you're done with that, see what you can do with 2. So you can go on to number 3 when you're done, but if you're not sure about this one, right? Most of your calculators, if you type it in, will do order of operations for you. The exception is the ones that only have one line on them. And so for those calculators, you got to do PEMDAS manually. So you got to do 15.5 squared first, and then multiply these. All right, so this is backwards of the previous one, right? So I'm going to start getting half of 1,500, and then what am I going to do with this 750? Divide. Then I get something like 9,800 equals v squared. Then I got a square root. So I get something like 98.99 or 99.15. All right. 4 and 5 are just a little bit, so they're the next layer of complexity that we're going to add to this, right? So 4 and 5 are examples of using that last equation we wrote down, the one that says work equals delta E. So here's what I do. Go ahead and start by doing a picture knowns and unknowns for 4, and then we'll talk about it in a second. So I got kind of a picture here, right? Well, let's get this in terms of knowns and unknowns. So you gonna give me a known or unknown, Gavin? Give me like one of the variables that I know. Okay, so that's my mass. Olivia, give me another one. Force is 15.6 newtons. Braden. What else? What is this 0.150? Distance. There's one other thing we know if you look closely. Anyone know what the other thing is? What do you say? Initial velocity, right? I start at rest, and I'm trying to find my final velocity. Okay? Here's how I do this, right? Pardon me. So work, in this case, is equal to delta E. And we know, right, we know that work is force times distance. I'm just going to plug that in on the left here. Give me a second. We got work equals force times distance on this side. And then you remember what delta means? Change in, which is which one minus which one? Final minus initial. And in this case, the kind of energy that I have, well, so if I start at rest, my initial energy is probably 0. And what kind of energy is my final energy? So it's moving. Is that potential or kinetic? I think it's kinetic, right? So this is my equation. Force times distance equals KEF minus 0, or force times distance equals 1/2 mvf squared. And then I can plug into that. That's what you're going to try and solve here. That's what I got. From there, see if you can do 5. Oh, am I wrong?
Yeah.
What is, sorry, what is it supposed to be? Okay, yeah, my bad. Definitely max. All right, cool. So I understand we're this equation is a little bit different. So here we've got in this case a trash can that's going 7.9 meters per second. And then it comes to a stop, right, at some point. What am I trying to find? What does it say I'm trying to find? Work, which is delta E, but yeah, I'm trying to find the work. We know that I start at 7.9 meters per second. We know I end at 0. And we know we have a mass of 10.2. So we're going to use the same equation we did last time. And remember, every time we do this, right, delta E just means final energy minus initial energy. Last time we said that work equals force times distance, but this time we don't care about force and distance. What are we looking for? We're just looking for work. So I'm going to leave it as work equals EF minus EI. What is the final energy? 0. And the initial energy is, well, it's whatever kinetic energy corresponds to 7.9, right? So it's 1/2 mVI squared, right? When I plug this in, I get 0 minus 1/2 times 10.2 times 7.9 squared. I'm getting negative 62.41, is that right? No, that is not right. 318.29, negative 318.29. Why is it negative?
Because it's traction, so it's actually.
Yeah, it's kind of pushing back against it, right? Yeah. Yeah, there are two ways to think about it. You can think about it directionally, right? The force is going against it. You can think about it, if it's stopping moving, right? What has to happen is energy has to leave the system. So the way energy leaves the system is by doing negative work. Any questions? I'm not going to ask you to upload that one. With this in mind, I want to ask a couple follow-up questions, just thinking about the equation. And then after this, I'm going to give you a little bit of a break. So here's the first question. Imagine two cars traveling down the highway that are the same size, same mass. However, the second car is traveling twice as fast as the first car. Which car has a larger kinetic energy and by how much? Tell your partner what you think about this. All right, I think we can all agree on the first half of the question. Which one has more kinetic energy? Part two, the faster one has more kinetic energy. Okay, that's, I think we can come to that. Grady, how much more does the second one have, though? Do you know? Twice as much? Fair enough. Going twice fast, twice as much kinetic energy. Do we agree with that? What do you think you want?
I would say that it is 4 times as much.
Why 4 times as much?
Because the velocity is squared, so there's twice as much velocity and that's also squared.
Okay, so we got to think about the equation, right? The equation is k equals 1/2 mv squared, right? So since velocity is squared, what that means, remember we kind of talked about this when we did the inverse square law with gravity, right? If you double velocity, right, 2 squared is 4. So if you double velocity, it's actually 4 times the kinetic energy. That makes sense. Double the velocity, it's 4 times the kinetic energy because 2 squared is 4. All right, next question for you to discuss with your partner. With that in mind, we've got 2 cars, but this time the second car is traveling 3 times as fast. How much more kinetic energy does it have? Tell your partner what you think. What? The music. Put me on the music. Yeah. What does that mean?
So it means
Like you auto tune?
No, like I'm gonna use the.
Oh, okay, sure. Scott, what do you think? How much more energy does that second car have now? 9 times. I could get 9. That is 3 squared, right? So the fact again that it's 1/2 mv squared means that if I triple the velocity, it's 3 squared, which is 9 times the kinetic energy. Ask you something slightly different. This time I've got 2 cars that are going the same speed, but one of them is twice as big. Okay? So same question, which has larger kinetic energy and by how much? They're the same speed, but one is twice as big. How are you thinking about this one? Okay, Audie, which one has more kinetic energy? They're the same. Tell me why.
Because they're going the same speed.
Okay, they're going the same speed, have the same kinetic energy. Lee, do you agree? They have the same kinetic energy? Which do you think is more?
I didn't decide that because I'm stupid.
Say what?
I said I didn't decide that because I'm stupid. But you have to have the math involved in the equation.
Okay, so the mass is the equation. So we know it can't be the same. No, that's fair, right? So we know it has to be the same, and it cannot be the same, all right? So which one are you saying then has more?
Oh, I didn't think about that.
If they're going the same speed, wouldn't it be the one with the larger mass?
Yes, the one with the larger mass has more kinetic energy, right? Because it has more mass in the equation. How much more kinetic energy does it have? Twice. Why is it not 4 times?
Because it's not squared.
Because it's not squared. It's 1/2 mv squared. Only v is squared, right? Mass is not. Yeah.
Let me say half more though. Because when you multiply the 2 by
I see why you're saying that, but the half occurs in both sides, right? So they both kinetic energy get multiplied in half. And since they both get multiplied in half, you got basically 1 times a half, which is 1, and 2 times a half. Sorry, 1 times a half, which is a half, and 2 times a half, which is 1, right? So it's still double the kinetic energy. That makes sense. Yeah. So yeah, so if I double the velocity, it's going to be 4 times the kinetic energy. If I double the mass, it's only 2 times the kinetic energy. All right, so this is the last question along this line of thought. So now I've got one that has 2 times the speed, but the other one has 2 times the mass. So simple question this time, which one has more kinetic energy? Tell your partner what you think about this one. Amy, which do you think has more kinetic energy? Why? Because it got twice as much mass. Fair enough.
Oh, wait, no, it's the first one.
Okay, why?
Velocity squared.
Ah, so you're saying that this one is 2 squared, so this one's 4 times, but this one is 2 not squared, so it's just 2 times. So the first one has more kinetic energy. Is that okay with everyone? Right. The first one has to have more kinetic energy because velocity is squared, mass is not. Right. So the first one has to have more kinetic energy. All right. I'm gonna give you guys a 5-minute break. If you need to go to the bathroom or get a drink of water, you can, but we're gonna start back up in 5 minutes.